Just want to make sure that everyone who's paying attention and doing the work should be passing, obviously. So that's what I'm going to do. All right, so this is topic number 4 or 5.
Maurizio's car slams into the concrete barrier, catapulting him out of the window and hurling him through the air.
All right, so the focus of the lecture is this guy. After he's being ejected from the car, notice that he keeps on flying forward, right? He's falling under the influence of gravity. So we know why he's falling. He's falling because of gravity. We get that. But the question is, why does he keep on moving horizontally? All right, what's pushing him in the direction of motion? You know the answer, right? Nothing, nothing. Nothing is pushing the guy in the direction of motion. There's nothing, absolutely nothing. Nothing is pulling or pushing on the guy in the horizontal direction. Yet this guy keeps on moving, right? He keeps on moving until he hits the ground. All right, so the question becomes why? And believe it or not, this was a question that people pondered for a few thousand years. This is not something that I came up with. This is Greeks, ancient Greeks pondered about it. And they thought that there was some kind of a push happening in the direction of motion. They called that the impetus. And then by the time we hit Renaissance, they thought that, you know, they knew something about air at that time. And they figured that, hey, well, this person is going through the air. It creates a vacuum in his or her wake. And then the air would just rush in right into that vacuum and just push the person in the forward direction. And then Galileo comes along. He says, no. He says, there's nothing pushing on this guy. There's actually nothing. There's no push. There's no pull. So if that's the case, why does the person keep on moving horizontally? So that becomes a question that we will address. Along the same lines, whenever a car accelerates in the forward direction, what happens to your body? You feel a push in the opposite direction of the acceleration of the vehicle, right? So the objects inside will always move in the opposite direction of the acceleration of the vehicle. So the question is why? You put the brakes on, same thing. The car is slowing down, and all of a sudden the objects inside will move forward in the opposite direction of the acceleration of the vehicle. Head-on collision between a car and an SUV. Who's going to be safer? You know the answer. The SUV driver is going to be safer. The question is why? You can come up with 3 reasonable explanations. Most people can on their own. You don't need to be a physicist. You know the SUVs are larger. Crumple zone is bigger. Bigger crumple zone is going to absorb the impact better. Translated to physics, that means it's going to generate a larger impact. It's going to generate a larger impact time. Larger the impact time is, smaller the acceleration is going to be. That's it. All right, so acceleration is what kills you, what maims you, what breaks your bones. So the larger the impact time is, the smaller the acceleration is, it becomes more survivable. What else? It's more massive. It's heavier. It's more massive. Somehow it helps. How? We'll investigate. Also, this guy is sitting higher up. All right, so he's not in line with the impact force. So that's going to help him survive this one. Immediately, the next question is, well, if that's the case, which vehicle is going to suffer a larger impact force? All right, so is it the car? Is it the SUV? Intuitively and commonsensically, you think that it's the car. If I were to ask you why, you're thinking that because you will say, hey, listen, it suffers more damage. All right, so the car is going to be a lot more damage than the SUV, and that's the reason why you will say it's going to experience a larger impact. Despite the fact that the answer is the same. Both will experience exactly the same impact. If that's the case, at that point, your mind just doesn't get it. How come this car suffers more damage then? All right, so these are known as the Newton's laws. There's a brief history. All right, so according to the history that Newton himself started, roughly about 350 years ago, this is more of a fiction than reality as far as we know. He came up with this story. According to this story, evidently he was under an apple tree when he was about 21, 22 years old, asleep, maybe taking a nap late in the afternoon. And then apple falls hits him in the head. And then he opens his eyes. He sees an apple hanging from one of the branches of a tree. And then next to the apple, he sees the moon. At that point, he starts to wonder, you know, he knows that the apples fall because of gravity. And his question is, why doesn't the moon also fall from the sky? All right, so that's the big picture. So that question becomes his obsession in order to answer that question. He comes up with 3 laws of motion. So that's the topic of discussion this week. And then he comes up with the law of gravity. So that's going to be a topic of discussion, I think, a week after next. And then along the way, he invents calculus. So that's Newtonian physics is what we're doing. So that's how the story gets started. All right, so the first thing he does, he borrows a law from this guy, Galileo. So Galileo lived about 400 years ago. Newton about 350 years ago. The year Galileo passed away was the year Newton was born in. All right, so it's a generation before Newton. Galileo came up with the law of free fall. So the free fall is something that he discovered. And he's also the inventor. This guy is the guy, father of science, not the inventor of science, but father of science. So how do you father science? It so happens, the only thing he had to do was he took philosophy as it was. I don't know, it's a 2-step process. You have the observation and you come up with a theory. And then once you come up with a theory, you apply logic to it. That's your philosophy. That's your Greek philosophy. That's the way philosophy was done forever. So he said, well, when you come up with a theory, just make sure that theory makes predictions so we can test it. So as soon as you have testable predictions, a way of testing these predictions, it turns into science. So Galileo is responsible for that step. So he turns philosophy into science. In doing so, obviously, he discovers free fall, motion under the influence of gravity, meaning that the objects, falling objects do accelerate, and they do accelerate at a constant rate under the influence of gravity. And in gravity, the acceleration is a value, right? That acceleration is a value, which is a constant value. So he was just trying to figure out how to measure that acceleration. Right? Because this guy came up with science, he's got a theory, he's trying to prove the theory, right? So how do you prove it? You got to make sure that it's expressed in a way that you can measure the prediction. So the prediction is acceleration, so how do you measure it, right? So the problem with trying to measure acceleration is, I don't know, it's the motion happens way too fast. Right? And most of you guys couldn't even tell when you drop an object, whether it was speeding up or falling at a constant speed. Now, this is 400 years ago. Right? They didn't have technology to measure something like that. So why not slow the motion down, right? So how do you slow it down? Well, use inclines. Right? So get a ball, place it on an incline, just let it roll down. Right? So that's one of the experiments that you will get to do at home. It's an interesting experiment. Also, you will find out how to compute or calculate or measure gravitational acceleration. So that's your next experiment, which is also coming up. So you will kind of follow Galileo in his footsteps. Anyway, so he's using an incline to slow down the motion. And then this guy's old, you got to remember, in the 70s, under house arrest, life is boring, and he's got his balls or marbles or whatever that he's rolling on these inclines, and then smart enough to know that he didn't want to lose his marble. So he erects a second incline to catch the ball and makes the observation that the ball goes back up to the same height, provided that you ignore surface force, the friction, right? All right, so he puts the incline further away, same observation. The ball goes back up to the same height. So he pretty soon realized that if you were to get rid of the second incline and let the ball roll, this ball is going to keep on rolling forever and it's straight line at a constant speed. And this question is why? All right, so what's pushing the ball in the direction of motion at a constant speed in a straight line forever? Knows the answer. He knows the answer. The answer is nothing. Nothing is pulling or pushing on this ball in the direction of motion. If that's the case, why does the ball keep on rolling? And his answer is straightforward, because in all appearance, the ball is going to keep on rolling in a straight line at a constant speed in the absence of any sort of external influences like a push or a pull. It's going to keep on rolling because it's got a tendency to do so. All right, it's got an innate tendency to do so. So the question is, where do you get that tendency from? All right, so this tendency of these objects to retain their initial motions in the absence of an external force like a pull or a push is known as inertia. All right, that's known as inertia. So Galileo is the guy who came up with the concept. And about a generation later, a guy named Descartes, a French philosopher and a mathematician, the guy who coined the term inertia. All right, that's it. So inertia, 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 which means that the object at rest, unless you pull or push on them, they remain at rest. That's what it means. And if something is moving to begin with, an object in motion, it's going to remain in motion. What that means is if something is moving to begin with, it's going to keep on moving. It's going to keep on moving at a constant speed, and it's going to keep on moving in a straight line. That's what it means, unless applied by an external force. Okay, so unless acted upon by an external force, unless there's a push or pull acting on it externally, this thing is going to keep on moving in a straight line at a constant speed. All right, so the question is, inertia, where do we get it from? Where do we get that tendency from? All right, so the answer comes from
Buenos Aires, Argentina, into the concrete barrier.
Answer comes from Newton.
Mauricio
So,
is at the back of the path. But as he
this guy is going to get thrown out of the car. Oh, go right through the seatbelt. All right, so the seatbelt is not going to be holding him in. He's going to rip through the seatbelt. And that's just, all right, he gets thrown out of the car, and nothing is pushing or pulling on him once he's ejected in the direction of motion. He's just maintaining the motion. All right, so he's moving probably close to 150 miles per hour. The car rolls over. He rips right through the seatbelt. He gets thrown out of the car. He keeps on moving horizontally along the X direction because he's maintaining his motion. He's maintaining his motion. All right, so the next question is, why did he rip through the seatbelt? All right, so if you were to replace him with a 6 feet tall feather, all right, same exact motion, same exact accident. The difference is feather is not going to get thrown out of the car because the feather is not going to be able to rip through the seatbelt. Why not? Because it doesn't have the same amount of tendency to retain its initial motion. Got it? So all of a sudden you realize that this tendency to retain initial motion is related to mass itself, right? And that's what Newton discovered. So we get our inertia from mass itself. So the mass is something that you can measure. So the inertia and the mass are the same thing, except mass is something that you can measure using a scale, obviously. So mass is your measure of inertia. So every time you measure mass, in essence, you're measuring inertia. So that's the measure of inertia. Proper units, kilograms, slugs in the British unit system. Of course, in the United States, we use neither. We end up using pounds. So we express mass in terms of its weight. So that causes all sorts of confusion. All right, so the big mass, big inertia, small mass, small inertia. So we go, oh, big inertia means something heavy, small inertia means something light. And so that connection causes all sorts of problems, all sorts of problems. Okay, so let's just address the problem first. Penny versus supertanker. Penny, light, you can flip it, you can put it in your pocket, you can jiggle it. Penny is a penny, it doesn't weigh as much. All right, supertanker on the other hand, this is 150 million pounds. It's heavy, right? That's 330 million pounds. This is 150 million kilograms. So that's 330 million pounds. That's what it means. All right, so this supertanker actually weighs more than the tallest buildings in the United States. We got one of them here in Chicago. That's the Sears Tower. That was the former name. Current name is Willis Tower, or Big Willie. That's what we call it. It's going to be heavier than that. So it's in water. It's heavy. If I were to give you a rope to tug on, is it going to move? Right. So that becomes the question. You know the answer. Intuitively, no, it's not going to move. If I were to ask you why, you would say it's not going to move because of a simple reason that, hey, it's heavy. It's heavy. All right. You can't move it just because it's in water. If you tug on it, it's not going to move. You know that. It's heavier than the heaviest building in the entire United States. It's not going to move. Just because it's in water doesn't mean that you can move it. And then I would say, what would happen if we were like take it out into space, like deep space where it's perfectly weightless? All right, so I can make it 100% weightless in deep space. All right. It's going to have still a little bit of a weight, but it's still going to weigh less than a penny. Just imagine that. And then that would probably construct a platform out of metal for you, and then put you on that platform with some magnetic shoes so you got your footing. And I would say, hey, listen, just tug on it. I'll give you the same rope. Will it move? Now, a lot of you guys are thinking, oh, now it's weightless. It should move. Yeah, it's huge. Yeah, it's huge. Don't get me wrong. This thing is huge. But it's like paperweight. It weighs less than a piece of paper. All right. It weighs less than a pen. It weighs nothing. Will it move now? You're thinking, yeah, why not? Why not? It should move. In the back of your mind, you're thinking you should be able to move it. You can push on it, pull on it. You can just grab the rope and then just spin and let go. Play hawk with it and capture it in video, and then maybe get tons of likes on TikTok. Just put it on TikTok, right? That's what you do. Will it really move? All right. Just because something is weightless doesn't mean that it's massless, right? Because your mind does a computation, two-step computation, because we express mass by its weight. If I were to ask you which one is heavier, the one on the left is going to be heavier, because you will think, and it's also more massive. Your mind does a computation when I say which one is heavier. You look at it, you go, oh, heavier one is going to be able to persist against the same force longer, right? Because the surface is offering a lot of friction. And so, which means that this is also more massive. All right, so you check to see what's heavy and heavier, and then based on that, you render a decision regarding which one is more massive. All right, so because weight is something you can feel, and then something is heavier, it's more massive. That's the way the computation takes place in your mind. Except what I did, I interrupted that thinking process. I made something weightless in deep space. And I was saying, oh, now it's weightless, I should be able to move it around. But you got to remember, just because something is weightless does not mean that that thing is massless. It's still got a mass. How much of a mass does it have? Well, it's 330 million pounds of mass. What do you think is going to happen? What do you think is going to happen? That's 330 million pounds that says, hey, pal, I'm not going to move because I'm at rest. So when you push up against it, it's going to offer a 330 million pounds of resistance. It's weightless, but it's not massless. And mass is a number that tells you something about a measure of tendency and the resistance that you will feel. And this thing still has a 33 million pounds of tendency to remain at rest. So what happens when you push against it? Well, you will end up feeling a 33 million pounds of resistance to motion under the circumstances. So what that means is the stuff that does not move here on Earth because it's heavy is still not going to move in space because it's massive. All right, so it doesn't have anything to do with its weight. All right, so that supertanker that you're pushing up against, that's the one that we will focus on shortly. If you apply a force on anything, okay, so what should happen is the force should overcome the inertia, any sort of force. It doesn't matter how big or small the mass is. If there's an applied force, there's an external force. The object should speed up, slow down, or change direction in the direction of the external force. Got it? That's what should happen. So speeding up, slowing down, or changing direction, it means acceleration. So if there's a force acting on anything, the force is going to cause an acceleration. All right, so the force acting on this mass is going to cause it to accelerate, and then the force is going to be expressed in terms of n, or it's going to be expressed.
下一则新闻是今天下午进行了中原总决赛，大家都在观看着，等待着这一个激动的时刻到来。这位选手，他已经做好准备了，大家报以热烈的掌声。他已经做好准备活动，两个眼睛紧紧地盯着这棵树。下一
All right, so force acting on the mass is going to cause it to accelerate. The other thing is, you kind of know this to be intuitively correct, but make sure that you understand it also explicitly. That the force, external force, and the acceleration will be in the same direction. Just get that. So this guy is going to accelerate in the direction of the force, right there. So he will accelerate in the direction of the force. So the objects will accelerate in the direction of the force, even if the force is invisible. All right, so the forces of nature will always be invisible. You cannot see gravity. You cannot taste it. You cannot smell it. You cannot even feel it. You think you can, but you cannot. Just take my word for it until next chapter. Right. So if gravity is the only force acting on it, you will feel weightless. All right. So how do we know that gravity is a force if that's the case? All right. So the falling apple, this is Newton's apple, will accelerate. Falling objects will accelerate under the influence of gravity. All right. And we know the direction of acceleration is in the downward direction, right? We also know that the force responsible for that acceleration will be in the same direction. So the force responsible for that acceleration will be in the same direction as that acceleration is. That's how we know that gravity is a force, despite the fact that we cannot feel it, we cannot see it. We can see the effect of it. The effect of a force is acceleration. So the falling objects accelerate, so which means that the gravity has to be a force, and gravity has to be in the same direction. So this allows us to be able to actually trace the gravity out to its source. Gravity can be traced all the way down to the center of the Earth itself. There you go. All right, so that's the only proof that we know that gravity is a force. All right, in Newton's theory, gravity is a force because anything that causes acceleration is known as a force. Even if you cannot feel it, even if you cannot see it, even if you cannot taste it, even if you cannot hear it. All right, you got 5 senses, and there's no way to detect gravity using your 5 senses. Get that into your heads. All right, so gravity is a freaking force in theory only, because it fits in with the definition of a force. What is the definition of a force? The definition of a force is what causes acceleration. Falling objects accelerate. They do accelerate in the direction of the external force. Even if you do not see the force, or if you cannot even sense the force with all your 5 senses, it is still a force because it causes acceleration. Welcome to Newton's theory. When somebody says gravity is a force, this is the reason why, even if they don't know why. Because Einstein is going to say, no, it's not a force, and Einstein is going to make it stick. All right. So by the time we get to Einstein, I just want to make sure that you guys are stepping through the history, because when somebody says gravity is a force, this is the reason why they say it is a force, because it fits in with the definition of a force, and it does so only in Newton's physics. All right, so in Newtonian physics, gravity is a force, you know, because falling objects accelerate, and the acceleration is caused by a force. That's it. And so the next question is, well, if gravity is a force, obviously you're able to explain why the apple falls. How come the moon is not falling? Well, it depends. Because it depends. Does gravity really extend all the way out to the moon? Let's check to see if that's the case. All right, so we'll take a look at the motion of the moon. It orbits the Earth, right? At a constant speed. But the direction is not constant. The direction keeps changing. So what would happen to the moon if there were no forces acting on it? In the absence of an external force, how would the moon behave? Now the moon is moving, right, already. And in the absence of any sort of external force, the moon would have gone in a straight line at a constant speed. It would have gone in a straight line at a constant speed. The moon is moving at a constant speed, but not in a straight line. So that implies that the moon is accelerating. So the question is, which direction, right? What is the direction of acceleration? We can kind of figure that out. Just checking to see which direction you will feel a push whenever you're driving on a curve like that. All right. So your body is going to get pushed away from the center on a curve like that, right? You will feel a push away from the center. So which means that the acceleration must be directed towards the center. Okay, so the only thing you have to figure out the direction of acceleration by looking at the motion of downstrapped objects inside the car. And I'm saying, wait a minute, the acceleration is directed right towards the center. So boom, you're done. Once you know the direction of acceleration, you know the direction of the force automatically. And I'm saying you realize that, wait a minute, the force that pulls the apple down, more than likely it's the same force extending all the way out to the moon, because this force is originating from the Earth itself, so it's this one, right? And the question remains and persists, but the apple falls, right? Well, why doesn't the moon if that's the case? Is it possible that this force is different? Why would I say that? Well, the reason why I'm going to say that is, number one, the apple falls, but not the moon. And number two, what happens when you place astronauts out in space? It feels like they're weightless, right? Where do we get our weight from, guys? You have weight. You get your weight from flow gravity. All right, so the measure of gravity, effect of gravity on you is known as your weight. So the measure of the gravitational pull is the same as your weight. So if gravity extends all the way out to the moon, you should not be weightless in space. All right, so obviously there's a force acting on the moon, originating from the center of the Earth, because if it didn't, the moon would have gotten a straight line at constant speed. All right, so the fact that the moon orbits the Earth implies that it's accelerating. That implies that there's a force acting on it, and this force is originating from the center of the circle. Obviously, there's a force acting on the moon, so the question is, what force? Is it the same force that pulls the apple, for example? Because if it were gravity extending all the way out to the moon, you would not be weightless in space. Yet these astronauts up here weightless.
Astronauts eventually adapt to their balance sensors, giving them confusing and unfamiliar information. After a short time in space, the human body actually forgets how to deal with gravity, and instead learns how to balance and move around without it.
According to NASA, these people up here are weightless because evidently they are weightless, or are they? We'll investigate. All right, so you're in deep space with that supertanker that we were talking about. So that supertanker is 330 million pounds, right? So you push against it, you push on it, against it with all your might. Let's assume that you can generate 200 pounds of force, single push, 200 pounds, right? Against this thing, which is 330 million pounds. Will it move? All right, so it's going to offer a tremendous amount of resistance. Okay, this thing is got 330 million pounds of mass that says, hey, listen, pal, I'm just going to remain at rest. It's going to offer 330 million pounds of resistance, but will it move? According to the second law, yeah, it should. All right, so force acting on any mass is going to cause an acceleration. But the force is 200 pounds, right? This thing is massive, 330 million pounds of mass, offering a 330 million pounds of resistance to change in motion. So will it accelerate? Yeah, but the acceleration is going to be unnoticeably small. It's going to be microscopic. I mean, if you could just push up against this thing for the next million years with the 200 pounds of force, it will probably go up to a mile per hour. Right? It's almost like watching the grass grow, except in extreme slow motion. This guy's going to go from 0 to something else, maybe 5 miles per hour, single push. This guy's going to speed up. So the question becomes, the fact that this guy is accelerating implies that there's a force acting on him. So the question is, where's that force come from? Where did that force come from? Where did that force come from, right? Where does it come from? You're thinking, oh, he's generating the force using his muscles. Nope. If that's what you're thinking, you're missing the point. The point that you're missing is, according to the second law, what causes acceleration is the external force, not the internal forces. Internal force meaning that you cannot generate an external force on yourself using your muscles. Okay, you can generate a force, but it's not gonna cause an acceleration. Okay, it's important. If you wanted to lift yourself up, you cannot grab the other arm and pull yourself up in the upward direction. You cannot pull yourself up by tugging on yourself in the upward direction. It's not gonna happen. You can try all you want. It's not gonna happen because it's an internal force. It's not gonna cause you to accelerate. All right, so all of a sudden you realize that the force causing this guy to accelerate in this direction has to be external to his body. So the quick logic shows you that this guy's applying a force on the spacecraft, right? So that becomes the action force. In turn, the spacecraft will apply the same force back on him. That becomes the reaction force. So all of a sudden you realize that the forces in nature will have to come in pairs, which means that they're always force pairs. For every single action force, there has to be an equal and opposite reaction force. And these forces will be equal to each other in magnitude and opposite in direction. And these forces will never cancel. All right, so the action force is acting on the spacecraft. The reaction force is going to be acting on this guy. So they're equal in magnitude, opposite in direction. And because they're not applied to the same mass, they would never cancel. Just remember that. That's one of the trickiest aspects of physics. So this becomes the third law. So Newton came up with the third law to explain how these forces come into existence. How these forces come into existence. He said for every single action force, there's going to be an equal and opposite reaction force. These forces will be equal to each other in opposite in direction. That's it. So what that means is, in any sort of impact or collision, it could be car to car, car to person, bus to person, train to person. It makes no difference. Every time there's an interaction between two objects, every time two objects come in contact with each other, all right, both objects will experience the same force. That's what it means. So the impact force is going to be the same regardless. Action and reaction forces will be equal to each other, and they will be in opposite directions. Taken to an extreme. All right, so taken to an extreme, this turns into a mind twister. So does this mean that when a person gets hit by a train, does this mean that the person applies the same force back on the train, even if that force is like 1,000,000 pounds? All right, so imagine that you're getting hit by a train at 60 miles per hour, right? And it's undeniable that the train can apply 1,000,000 pounds of force, 1,000,000 pounds. Okay, no one disputes that, and the evidence will be fairly obvious. All right, and if you're watching someone, if you've ever seen someone get hit by a train at 60 miles per hour, this person is gonna just break apart. Torso goes one way, head goes in a different direction, legs, arms splatter all over the place. It's nasty. All right, that's no one denies that train can apply that amount of force. So the question is, will the person apply the same force back on the train? Now, according to Newton, the person should apply the same force back on the train. Right? According to Newton, yes, that's the third law. Well, where is the evidence? Okay, where's the evidence that the person applies the same force back on the train? All right, so I usually get some real silly answers from students. Oh, well, evidence is that there will be a blood splatter all over the place. No, that's no evidence. That's just, well, what does it mean? The only that means the train applied a tremendous amount of force on the guy. Where's the evidence that the guy applied the same force back on the train? All right, because just think about it. When was the last time you were able to apply 1,000,000 pounds of force on anything, and how well did that work out? So where's the force? Where's the evidence? Train is not going to dent, obviously, so they're not built to dent to increase the impact time. So where's the evidence when you apply the same force back on the train? Well, the evidence is going to be in the acceleration, right? So what is the effect of a force acting on a mass? Acceleration. So what is the acceleration of the train? If there's 1,000,000 pounds of force acting on it, what would you expect? What would you expect? You're on the train, minding your own business, drinking your coffee, texting, or reading a book, and doing something, listening to music. If a train hits a person, with 1,000,000 pounds of force, would you even notice it if you're on the train? Think about it. Would you notice it? And kind of intuitively, you know the answer. Like, no, unless you saw it happen, unless you see it happen, you're not going to notice it. And if you didn't see it happen, you may end up seeing your head flying by. But you're not going to make the connection, because when was the last time you saw a head flying by in your life? Hopefully never, right? So you're not going to make the connection. You're going to look at the face and think to yourself, look at that ball, which is a face on it. And then the next thought is, oh, gee, the Halloween is coming up. That just reminds me. Where can I get one of those? Because you're not going to make the connection. It's just not possible. So how is it that the person applies the same force back on the train and you don't even notice it unless you saw it? And the reason why you don't notice it is because train is incredibly massive, just like that super tanker is. Except super tanker is a lot more massive than the train. All right, these trains, I don't know, it's like 10,000,000, 20,000,000 pounds, sometimes 50,000,000 pounds, depending upon how big the train is. And then you apply a force on the train, which is about 1,000,000 pounds. For a fraction of a second, like 100th of a second, sometimes 1,000th of a second. What do you think is going to happen? So the action force is acting on something really not so massive, something which has very small, very little mass. The reaction force is acting on something which is extremely massive. The forces are the same. This is extremely small mass. This is a huge mass. So they experience the same force, except the smaller the mass is, the bigger the acceleration is. So, and bigger the mass is, the smaller the acceleration is. So this is the acceleration of the person. Maybe it's going to be 1,000 Gs. Here's the acceleration of the train. It's going to be really small, so small that the train is probably going to go from 60 miles per hour to 59.999 miles per hour within the duration of that impact. So the acceleration is going to be unnoticeably small. That's it. That's what you would expect. All right, so mathematically, not that you will have to do the math, just understand the results of it. All right, so we'll have a person who's going to get hit by a train at 60 miles per hour. So a train is going at 60 miles per hour. Train is massive, person not so much. Impact time is 100th of a second. All right, so acceleration of the person and the train and the speed of the person and the train. All right, so what do we expect? We expect the person's acceleration to be deadly. Train is going to be unnoticeably small. If the train is moving at 60, the person getting hit is going to move double the speed of the train. All right, so that's based on the conservation of energy momentum principle, something that we will touch on later. And then we don't expect the speed of this train to change that much. All right, so the action force acting on the person, reaction force acting on the train. Because of the action force, the person is going to accelerate. Because of the reaction force, the train is going to accelerate in the opposite direction. So acceleration depends on the force and depends on the mass. A smaller mass is going to accelerate more. So they will have the same force. All right, mass of the person is small, so the acceleration of the person is going to be relatively large. In this case, it's going to be 500 G, so that should be deadly. All right, so same force acting on the train in the opposite direction. Train's mass is in millions. So the acceleration is going to be unnoticeably small. It's a very small acceleration. All right, it's a simple jerk, it's a vibration. And train vibrates all the time. All right, so speed of the person should be double the speed of the train. So the person initially is not moving. Train is moving at 60. So after the impact, the person should be moving about double the speed. So it should be about 120 miles per hour. And we don't expect that much of a change in the speed of the train. So the train was going at 60. It's going to be about 59.99 something. So you plug the numbers in, and that's what you got. It's small. All right, so the acceleration of the train is going to be unnoticeably small. So it's, which means the train is going to keep on moving at 60. So does the person apply the same force back on the train? Absolutely. All right, and predictions of the theory bears themselves out. All right, so the person is less massive, accelerate more. In fact, the acceleration is going to be deadly. Train is extremely massive, and the acceleration is going to be unnoticeably small. Action and reaction forces are the same, so they will both experience the same force. Head-on collision between a train, between a car and an SUV. All right, so which one experiences a larger impact force? It's the same. The SUV is going to be better off because it's more massive in essence. All right, so same force, larger mass, smaller acceleration. Acceleration is what kills you, what maims you, what breaks your bones. Small car, smaller mass, same force, larger acceleration. So once again, the acceleration is what kills you, what maims you, what breaks your bones. So which means that the car driver is going to be worse off in this encounter. All right, so there's one thing that we didn't address. Let's just address that. I just skip over something crucial that needs to be emphasized because it's going to come up again. Unstrapped objects inside vehicles. All right, so when you accelerate, unstrapped objects move backwards, right, in the opposite direction. So car speeds up, the fly goes in the opposite direction. You put the brakes on, car is slowing down, the fly's gonna go in the direction. So the question is,
So quick, remarkably agile. Lexus.
why does the downstrapped objects keep on moving in the opposite direction of the acceleration of the vehicle? The answer to that question is they keep on moving in the opposite direction of the acceleration of the vehicle because in the absence of an external force acting on them in the direction of motion, they're not able to keep up with the acceleration of the vehicle. All right, they're simply maintaining their initial motion. All right, so in this case, for example, the car accelerates forward because there's a force acting on the car and there's no force acting on the fly. So fly is maintaining its initial motion, and relative to the fly, the car is actually speeding up. All right, and relative to the car, relative to the fly, the car is speeding up, and relative to the car, the fly is moving in the opposite direction. And relative to the car, it looks like the fly is actually accelerating in the opposite direction. And then when you put the brakes on, the car is slowing down because there's a force acting on it, and there's no force acting on the fly, so the fly is going to keep on moving at a constant speed all the way up to the windshield. So the objects inside they will move in the opposite direction of the acceleration of the vehicle because they're simply maintaining their initial motions. All right, so this happens because of inertia. All right, guys.
And their ability.
That's pretty much it. All right, so this concludes the review at this point. All right, so does anybody have a question or comment or anything that you want me to explain or address at this point? All right, so I'm going to make the next week's lecture available this week. All right, so once again, let me just go over the basics. Okay, so those of you guys who are taking the labs, in addition to this one, obviously there's a lab component. I'm going to be grading the first lab. I'm going to make the second lab available this week. Okay, I think the second lab is going to be related to gravity. It's going to be related to free fall because that's already made up. All right, so I'm going to give you guys labs every other week until the end of the semester. So they will be take-home labs. Your tests are multiple choice. Okay, and they're not as easy. So you got some knowledge-based questions, and some are questions that require deeper understanding. So because these are conceptual problems usually. And so 7, if you're getting 70%, that's a C. 80% is going to be a B. 90% above is going to be an A. So I don't want you to get anything less than a C. So if you get less than a C, if you get less than 7 on these tests, upgrades are available. On upgrades, you got 2 attempts. Okay, so I'm going to keep it higher of the 2 attempts. So that's what I do. If you score 7 or better, 70% or better, that'll give you 70% for that particular test. All right, and that's the way it's going to be until the end of the semester. So we will cover 1 topic per week. We will keep doing it. and then you will have your weekly test. And if you, for whatever the reason, if you fail, just do an upgrade. At the end of the semester, you can do the final test. The final test is the same as regular test. I think on the final test, I'm going to have 15 multiple choice questions. And the questions are the same questions. Okay, that's my test bank. Okay, so as long as you're getting better and improving, when you take the final test, it's an optional final test. If your final test grade is better than your average test grade, it's going to replace it, which means that you can struggle all throughout the semester, you know, just getting a passing grade per se. And then after a while, you realize that you're getting better at it. And then you take the final test, you can score 90% on the final test. That 90% would replace your average grade up to that point. So which means that your average grade would be 90% up with the NA. So just keep up with the work. Another thing that I want you to do is, I mean, if you have questions or whatever, okay, just hold on to those questions. Either email me the questions the night before, or ask me those questions, like clarification questions. You know, you take the test and then you should be able to see the answers after the deadline. And then all of a sudden you're looking at the answer and then the answer is not making sense to you. So you can ask for an explanation. I'd be more than happy to go through these test questions with you so you have a better understanding of how to do these things. All right, so just email me the night before or just show up if you're not working, obviously. And then ask me those questions during the recitation session. All right, so this is it for this week. So next week, the lecture is going to be on net force. So it's going to be related to frictional force and that sort of stuff, the apparent weight, the frictional force. All right, so these videos are mathematical. Obviously, I'm not testing you on the math, but be able to understand the formulas and understand the conclusions. It's important, all right? Because a lot of these questions come out of your understanding of the concept. Be able to look at the formula and understand what the formula represents is also important because these formulas, in essence, are summary statements or whatever it is that we're discussing. Got it? All right, so that's it. Does anybody have a question that you want me to explain or clarify at this point? All right, so, all right, Carly, do you have a question? Carly. Colby, John, anybody? All right, so if you guys don't have any questions, hope to see you guys next week. That's awesome. All right, guys, take care. You're welcome, John. All right, guys. Bye.